multi-type branching processes and give talk about the computing the extinction probabilities. That will be one part, and the second part will be I'll define an extension where you have also decisions. So it's branching processes are purely probabilistic. So a model where you have probabilities and you can make some choices, and then discuss about optimizing the extinction probabilities. So branching processes, I mean, it's an old model. So they were first introduced in the single type case by Galton and Watson in the 1870s. At the time, the original motivation was Galton wanted to trace the look at the extinction of the names of the British aristocracy. So that's defined these processes and studied them, what the extinction probability was. And then was later generalized to the multi-type case, and the basic definitions and theory was developed by Kolmogorov and his students in the around 1940s. There were previous isolated occurrences of it. And they have applications in biology and other areas. So it was, I guess nuclear chain reactions was one of the early applications. And there is many papers and books. Here I have put some books about applications in biology, and there is also many books about the theory and the mathematics of branching processes. So that's a very well-developed theory. So the question is, well, what's there more to say after all of this work? So basically, if you look at them, with the basic algorithmic questions, like how do you compute the extinction probabilities, really doesn't seem that there was no good solution. Good in the sense of how we consider good in computer science. So let me define the basic multi-type branching processes. You have a bunch of types, so 3 types in this case. And for every type, we have some probability distribution of what the offsprings of a creature with that type is going to be. So the green one with probability third will have 4 children like that. Probability half will have a green and a brown child, and probability 1/6 will have no child. And the same for every other one. We have some probability distribution of what their offspring was. This, for example, could be species, could be bacteria with, there are different alleles for a gene, and you have one allele, there is some probability it dies, the bacterium dies. For some probability it divides with exactly faithfully, and some probability that there is a mutation in one of the successors. So we are given this specification of what the process is, and if we start with one individual picks at random one of the rules. He has children. Each one of them, independently with some probability, has its own success, its own children. So this, and they may be different kinds. This one had 2 green children. This one had no children, and it's following generation, the same thing happens. Each one of them has one rule activates, has its own children. The thing goes on forever. Maybe it goes on forever, or maybe at some point it stops and the process finishes. It goes extinct. So we would like to know what's the probability of eventual extinction if you start with one individual, or if you start with some population of individuals. So we can define for every type, we can define the probability of extinction. If we start with one individual of that type, we would like to compute what these probabilities are. Well, one thing we could do is run a lot of simulations. Start with one, run many runs for many generations, take statistics and see what that gives you. But we would like to get something more accurate. And the theory of branching processes tells us what equations this quantity satisfy. So if we look at every type, we can write down an equation that this has to satisfy. So the probability of extinction of the green type, well, with 1/3 probability, we'll have these children. And since these develop independently, for this to go extinct, in that case, each one of these must go extinct. So in that case, the probability will be the green probability times the square of the brown times the purple. Plus 1/2 here will be the product of the green and the brown. Plus 1/6, in this case, it dies right away. So there is one equation for the green, one for the brown, one for the purple. And the probabilities we're looking for satisfy this equation. So it's a solution to this set of equations. It's a fixed point set of equations that express what we are looking for in terms of itself. You know, that's the nature of the recursive process, is that you express it in terms of yourself. Now, these equations in general may have several solutions, and it's the fact that the solution we're looking for is the least non-negative solution. So the extinction probabilities is the least fixed point of this equation, and there is least fixed point in the sense that it's a solution which is smallest in every individual coordinate. There is such a solution. So in this example, for example, it's approximately that's what the solution will be. So in general, these are some numbers. We would like to find these numbers.
Is it easy to see why it's the least fixed point we want?
Yeah, it's actually easy to see it. So let's look more generally. What kind of equations do we get here? So on the right-hand side, we see these are polynomials. The coefficients are all positive. And in fact, they sum to 1, because these are probabilities for each rule. So these are probabilistic polynomials. Okay, so in general, it's a set of equations. We'll have a set of equations in n variables, where every polynomial is monotone. We'll call it monotone. The coefficients are positive. And it's probabilistic. The coefficients sum to 1, or can allow also at most 1 more generally. So an example is the set of equations you get from multi-branching processes. And there is other models where we get exactly the same equations. Stochastic context-free grammars is another type of model that's used in natural language processing in other areas. It's a subclass of recursive Markov chains, gives exactly the same equations also. So for computational purposes, we assume that all the input numbers, we are given a specification of a multi-type branching process, the types and the rules. We assume all the probabilities, the input numbers are rationals, given in binary. And we count the input size. As usual, we count it as the total number of input bits to specify the instance. Now, in general, since these are nonlinear equations, the solutions are irrationals. So we're not going to compute them exactly, but we want to compute them up to desired precision, so many bits of precision. Now, why there is a least fixed point? So it's the fact that these are monotone polynomials means that this vector P of polynomials defines a monotone mapping, actually from the unit cube to itself. So by Tarski's theorem, it has a least fixed point. As if you have a monotone mapping that's bounded, it has a least fixed point. So a solution that's smallest in every coordinate. And it's a fact that for this particular model, for the branching processes, the vector of extinction probabilities is the least fixed point. And also for these other models, the quantities we want to, that I mentioned that are modeled by these equations, the quantities we want to look again is this least fixed point. So the question is, can we compute those in polynomial time in the input?
You would start at 0 and iterate the equations. Would that be a...
Very good.
What's wrong?
Good. So one solution, and this is actually the common solution, is you start at 0 with a 0 vector, and you apply repeatedly this operator P. It will have the property that it will converge monotonically to the least fixed point. So the question is, how fast does it converge? The thing is that in general it will converge very slowly, even in simple examples. For example, if we take this simple example where this one splits to two children with probability half and dies with probability half. So we get this equation. And the least fixed point for this equation, you can see 1 is a solution here, and in fact this is the least smallest solution. So, for this we'll have the property, so the right answer is 1, but it's not difficult to see that in order to get I bits of precision, k bits of precision, you will need roughly 2 to the k iterations to get that.
This is the marginal case. I mean, if you made it any deviation away from this, you would converge exponentially.
For this particular example.
Yeah.
So if you change these probabilities, you mean.
Slightly, yeah.
Right, yeah. Question?
Is that not true in the general case?
No,
That
it's
if
not.
you sample a polynomial number of nearby processes, that most of it will converge exponentially.
Right, and remember that we have also a multi-dimension. So this is a fixed complexity. Theoretically, that's a fixed instance. It's one type with one specific simple case.
But isn't the manifold critical cases of lower dimensionalities?
In some sense, yes, right, yeah. Question? In general, this is a simple multi-type. So in general, in the case of multiple types, can be worse. You can have instances where to get the first bit of precision, to get 1/2, you will need exponential number of iterations. What's another way to tackle? So the algorithms I'm going to talk about are actually quite simple, and we all kind of knew them. The analysis is the non-trivial part. So the big workhorse for this kind of solving equations, another big workhorse is Newton's method. Okay, that's a Swiss Army knife, another big, older Swiss Army knife of an algorithm solves all kinds of problems, linear programming and fixed points and everything else. So Newton's method, so I assume most people know. For those of you that don't know, the idea is that you iteratively start from some point and then get to new points by iteratively you take your function, the right-hand side, you take your function that you want to find the solution and do a first-order linear approximation. You pretend it's a linear function, so it's a first-order approximation around your current solution. Then you treat the linear function and you solve a linear system, which would give the solution if your function was linear. You take that as your next point and do the same thing there and keep going on and hope that the thing is going to work. So this is basically the equation, but that's what we're doing, solving a linear system to find out what the next point is going to be. Now, generally it depends where you started from, that's one thing. And generally it depends, you have to, in order to be well defined, you have all the points, you have to have a non-singular matrix to invert. And it depends, what the algorithm will do. It depends on the instance. It may go around and wander around and not get anywhere. It may converge, but not converge to what you are looking for. So it can have all kinds of behaviors. So what does it do in this case? Well, we take a monotone polynomial system, so not just probabilistic, so just positive polynomials. Well, first we have to identify the variables that will have value 0 and remove them, because if we don't do that, it's going to run into singularities. So we find the variables that have value 0, and that's actually very easy to find. It's simple and/or reachability for graph theoretically. So that's very easy to find those that have 0 value. We remove them, and once we do that and we start, we can either apply directly, or even better, we can decompose the system into strongly connected components and apply Newton component by component bottom up. starting from the zero vector. And if we do that, it has the property that it's always well defined. It's not going to run into any singularities. And the iterations will be monotonically improving and converge to the optimal solution, to the release fixed point.
Strongly connected components of the graph of the equations.
Dependencies, yeah, of the equation. So you do like a dependency graph of which variables depends on whom. You work your way up.
So I guess the matrix that you had in the previous slide is not PSD, right?
No. So, yeah.
Otherwise things would be easier.
Yeah, so it's just you take, the it's polynomials, you differentiated them.
It's a variable.
Yeah. Yeah, and the instantiations, Yeah. So basically what really Newton is doing is it's kind of shortcutting every iteration of Newton, it's shortcutting many iterations of the P operator. And so you can prove actually that this dominates strictly the P iterations and significantly. And it converges to the right thing.
You didn't tell us anything about the complexity.
I didn't say anything about complexity. So the question is how fast does it converge? So this actually has been implemented by a couple of groups. And, in some, experimentally, they have done some large benchmarks from natural language processing. These people are from NLP. And some random instances seems to work well. Is it polynomial time? Well, it turns out it's not. So Esparza et al. Actually looked at it closely and so found bad examples. So there are probabilistic systems and branching processes for which Newton will take an exponential number of iterations to get the first bit of precision. In other words, to get distance a half from the actual value. And once you get the first bit, it works pretty well, even in these bad instances will work well. But it's...
The degree of the polynomial in those instances large, or
No. So basically, you can reduce everything to degree 2 if you can do the whatever. It's easy to reduce every polynomial to the quadratics. Yeah. So the degree doesn't really matter. Yeah. But the sort of thinking about looking at the hard instances, it is sort of, and the intuition is there that the hard cases are the critical cases where you have one variable, variables that are just on the critical, at the boundary. They have value 1 and make difficulty, where it's hard to do it. So we'll see then. So the result is that we can actually approximate by just a little bit, paying attention. We can approximate the least fixed point to any desired number of precision in time polynomial in the size of the input, so the size of the description of the branching process or the system, polynomial system, and the number of bits of precision. So the algorithm is quite simple, actually. And so we process the system, remove value 0, but also identify and remove the value 1 variables that have value 1 in the solution. And to find the value 1s, it's not very difficult. It's really relies on the theory of branching processes and some graph theoretic processing. Basically, it's you look at certain matrices and look at their top eigenvalue, and there is also characterization by Kolmogorov-Sebastianov that in the nice strongly connected case or positively regular case, the telling whether the value is going to be, the extinction is going to be 1 or not depends on the spectral radius of that matrix, whether it's bigger than 1 or not. And basically using that and then working, doing the consequences component by component, you can basically identify all the variables that's going to have value 1, where extinction will be for sure, and the other ones. So that's the first step, is to identify those and take them out of the equations, plug in their value and take them out of the equations. And then we apply Newton, the reduced system starting from 0. And the theorem, and sort of the non-trivial part is to prove that theorem, is that then if you do that, after a linear number of iterations, Newton will actually get you, to get within j-bits of precision, it suffices to run some linear amount to the input size plus j. So that's almost gives a polynomial time algorithm. It's not quite a polynomial. What's the reason that we can't quite claim from that polynomial time?
Huge numbers?
It's that the numbers get big. So when you do operations, if you want to do exact arithmetic, the numbers are going to grow exponential. So it's polynomial in the unit cost model of computations, where you charge unit cost for every operation, no matter how big the numbers are. So to actually have polynomial time, you have to truncate, and then you have to do the truncation properly. So it's what we do is we round down, and the down is important, that you round down as opposed to whatever. So we round down all the numbers as we go along to a polynomial precision. And because of approximation, some numbers may get negative, then you just have to force them at 0 if they try to become negative. And if you do that, then it's going to work properly.
Is the computational complexity of the eigenvalues of those moment matrices folded in here?
Yeah, so the computation, computing the eigenvalues is polynomial time, right, yeah.
So
Yeah.
H stays the same throughout the...
Yeah, so this H stays the same, so the precision to which we compute it, right? And doing that, so we can still show that this doesn't actually change things. Still a number like the same number of linear iterations is enough with the approximation to still get you within so many bits of precision. So that's the algorithm. It's basically it's identify the 0 case, the value 0. That's easy to do. Identify value 1. You do some eigenvalue computations. Take them out of the picture, and then run Newton with rounding down and keeping it positive, and then it's gonna converge it.
When you're identifying the variables that have value 1, your test was based on the spectral radius, and you don't get a boundary case there when the spectral radius is exactly 1, and you have to decide.
Yeah, so that's not a difficulty. Yeah, I mean you can. So we identify. So to identify whether what the spectral radius is, not what it is. You just have to compare with 1.
Yeah.
You take them out and you kind of propagate and do several matrices along the way. You have to do it. And then once you identify the 1 variables and you take them out, then you can run Newton.
So you're doing something like a Stern test to determine whether there's a group greater than 1? I mean,
No. It's you can do it. One way is to do it with linear programming. To tell whether the eigenvalue is going to be 1 or more, you can do it with linear programming. But in this special case, you can do it also easier with. So in our paper, we did it with linear programming, and then there's another paper of Esparza and some other people who actually show how to do it also with linear equations. So you can do it without doing anything fancy.
So if you want to know more about branching, for instance, you want to know distribution of numbers of copies of some type, it's basically the same formula, the same calculation, but you might, as I understand it, to get a generated function, you need to start with complex numbers in iteration. Is it then the same algorithm you use?
So I'm only talking about the extinction probabilities. The question is, what else can you do with those? So generating functions in general will get a big mess if you try to manipulate them, especially the multi-type case. They're going to explode right away. So you'll need to find a way to do it without doing that, treating directly the generating functions.
You have done something.
Yes, but I couldn't say that it wasn't a big mess at the end. I mean, it seems to be substantially harder to do than to get the extinction. I just wondered if you had some clever algorithms to help.
Yeah. So, well, at the end, they'll leave as an open problem and do other things.
But you can also do generating function for positive arguments, and then you can then get out. You can still infer a lot of things.
But with generating functions, it's gonna explode, right? I mean, you take it through, a few iterations, it has become exponential. It's gonna, grows very quickly. It's a multivariate polynomials. You plug them in the cells, they grow, very rapidly. So you're not gonna get any bounds.
No, but
like that.
you're looking for distributions since there's no steady state except extinction or going to infinity.
Oh, the
You're looking for
infinity.
distributions of some finite
So
time.
in terms for the infinite, for the limit distribution, we know very well what it is from the
Right.
theory of branching processes.
Right.
Yeah.
So one's interested in the case where it's a long but finite time.
So if you have a
Distribution.
particular finite time, yeah. So this is one of the concrete questions. How can you, given a time n, can you calculate what is the distribution? So that may or may not be easy. We don't know. I mean, I don't know.
Are the second or higher moments figuring into this algorithm?
Not really. So the algorithm is just the straightforward. It's there. Once we have cleaned the system, it's Newton. And to Newton with rounding, nothing to it. The analysis involves has computing bounds of matrices and lots of stuff. So maybe I'll say one. Had a question?
Yeah. So how does H relate to the approximation accuracy?
Yeah. So H is where do I have H?
The theorem.
Yeah, this is H. Yeah, so H is, depends, it's a linear in the size of the input. And the approximation, and the number of bits we want to get. I'll just say, I mean, there's no time to go through the proof, but just the key idea of what's happening is, first of all, it's what's important. One thing that's important is to keep always the solution, the candidate point between the zero vector and the least fixed point, and we'll work our way from zero to least fixed point. And then for these points, for this cone, there is has the property that the spectral radius of the derivative matrix, the Jacobian, is negative, is less than 1, so you can always invert. You don't run into singularities. And then what happens is that there is like a progress that's made that in some sense the ratio of how far you are from the fixed point versus how far the fixed point is from the one vector, it essentially gets halved in every iteration. So you are making like good progress in every iteration in that direction. And the other key property is that the least fixed point cannot be very, very, very close to 1. There is a gap there. So if the extinction probability is not 1, if you have a probability of survival, it cannot be minuscule. The probability of survival is 1 over exponential. Whereas it's possible that you have minuscule probability of extinction, that you almost surely survive except for a minuscule probability. So the probability of extinction could be doubly exponential small. So the solution could be 1 over 2 to the 2 to the n. But it cannot, the probability of survival cannot be 1 over 2 to the 2 to the n. It has to be 1 over 2 to the n.
Right.
So there is a gap there, so you keep halving it, and that's why it takes a linear number of iterations to get there.
So your things near survival are again easier, harder than these linear restrictions.
Yes, right, yeah. So there is like an asymmetry there. So now that gives you an approximation to the extinction probability to any decision you want. If you are dying to know, is the extinction more than a half or less than a half? So if you want to do a sharp comparison with a particular value, that looks like a harder problem. So if, let's say, knowing that the probability is 0.49999, and you would like to know is it really 0.5 or maybe 0.500001, that's a harder problem. It's a particular, it has to do with what I said, how do you deal with big numbers, doing operations on big numbers? So, for the computer scientists among you, it's complete, you can call it complete, for unit cost polynomial time. In other words, you can do it in polynomial time if you charge unit cost per arithmetic operation. And if you can do it in polynomial time in the honest model where you count bit operations, then you can do any other decision problem. So it's as hard as any other problem.
So it's space complete.
It's not space complete.
Is not this way?
No. So that's Pericles, I guess, knows a lot more complexity. So there is a subtle thing here about this is unit cost rational arithmetic model as opposed to having the floor operator. With floor operator, unit cost gives you actually p-space. Without the, if you have rational arithmetic, then it's not actually p-space, but we don't know what it is. But it's, I would bet that it's not real polynomial. If it was actually honest polynomial time, that would be fantastic, that you could just count arithmetic operations and not worry about bits. That would be, but I don't think it's true. So that's probably you can do.
Do we know which conjecture this is close to? Which other?
Other like PNP?
Like collapse of hierarchy?
No, we don't have. I don't know anything like that. But there's a fine distinction, and I don't think I don't know that we really die to know if it's, how does it compare exactly with a number as opposed to what is it approximately.
Linear programming.
Yeah.
Just even then, for linear programming, it's still open.
For linear programming is open? Sorry? Oh, the strongly polynomial, you mean, that question. Yeah, that's another question there. So then let me say a little about the model where you have some choice also.
Just a quick question. So what exactly is it about this branching process that makes this work as opposed to any polynomial who's trying to use which point you're trying to find?
So it's an important property, this probabilistic polynomial. The fact that the coefficients sum to 1. That's a key. That's an important property.
So you can do this for any polynomials whose coefficients are non-negative and sum to 1?
Yes. So that's for all probabilistic polynomial systems. Right. Yeah, or less than 1.
So this is more general than just the branches?
You can actually show it's equivalent. So you can go the other way around also. So you can define the branching processes that do that also. Yeah. You have to worry a little bit about the high exponents and stuff like that. But it's formally there is a reduction the other way. So we define then a generalization where you suppose you have a branching process, but it's not all probabilistic. So you suppose you can have some control about what the process is going to do. So there is a set of possible actions for each type, things that you could do or that it could do, which will affect what the distribution is going to be. So, for example, in this case, let's say this creature can decide, let's say, to eat vegetables and then will have a green child, or eat junk food and then it's going to have a brown child. More generally, you could have, the others here in the picture are probabilistic. In general, each entity of a given type there could be several different actions, and for each action, you get some probability distribution. For example, you raise the temperature, then we'll have some distribution of children. You lower it or you give it a medicine, you'll have some other distribution. So we have a specification like that. The objective is to minimize or maximize the probability of extinction or survival. So we want
of one particular type.
Of all particular types, so every type has, there is some actions, and maybe for some there is no choices, for some others there is choices. So the process starts with some initial population, some individual. They have some, we choose some action, or maybe that creature chooses an action, has probabilistically the children. Each one of the children chooses an action, has probabilistically a set of children. The process continues, and the goal is to optimize extinction.
But can you have some creatures that want to maximize the probability of extinction and the others that want to minimize the probability of extinction?
For this, we don't. So it's they all want to maximize extinction,
Or minimize?
well, presumably they want to maximize survival probability. Okay, if they are doing, looking for their own good, they want to maximize probability of survival. If we are controlling it that it's a virus or something, we want to maximize the probability of extinction, minimize survival. So for all, it's the same thing. Now, I know what you're asking, and that's another extension, where if we have some want to do one thing and some want to do another thing. Okay, so maybe at the end, I'll say what happens in that.
So what can the decisions depend on?
So the decisions can depend pretty much on everything except their own children. So they can look what happened in the past, they can look at who else is around, they can take randomized actions if they want to flip some coins on the actions they have available. They cannot depend on their own future. They can depend on anything else.
Presumably they can't depend upon their cohorts, future either.
They can depend on the cohorts. They can depend on the other siblings and other things. Yeah. So we allow them to depend.
But how do you define them? There must be a consistency condition, right?
Well, so let's say if the one situation could be. No, yeah, you can depend on your own descendants. So it could be that, let's say, if they think it's asynchronous. By the way, for this does not matter, for the extinction probability in particular, it does not matter if you have discrete process or with discrete time or continuous time, because it's the same really because of independence. But let's say if you have the discrete process where you go generation by generation, you are allowed, everybody is allowed to look at the others and decide what to do.
No, I mean,
That's okay.
If I will have a child, if and only if my brother has a child.
Yeah, it cannot depend on the action. Yeah, they cannot depend on, cannot coordinate actions.
I can see, no, but you said you can depend on others' children, right?
No, it depends on others.
On their history.
Yeah,
Okay.
yeah, and who else is alive and things like that.
But you can't condition upon the decision depend upon what the total population is at that time, for example.
Oh yeah, you can look exactly at what population is available at that time, what the composition is, at whatever. But all of this really don't matter. All of this really don't matter because the property is that there is an optimal deterministic static policy. So there's an optimal policy where everybody of the same type does always the same thing. So all the creatures of the same type do always the same thing. So no randomization, and you don't really need memory. It's totally memoryless. Another property is that the local search algorithm is going to converge. So if you start, every type starts with an arbitrary policy, arbitrary action, that's their policy. And then at every step, you repeatedly, a type looks to see if they can, there is a better action available, that if they choose another action, given what everybody else has chosen at this point, if they can choose a better action,
so
then
they
improve.
use the previous algorithm they use the first algorithm?
Well, they don't even have to optimize. They can use the previous algorithm to do this checking, right? Yeah. So they see if there is a better action available. If there is, they choose it. They don't have to choose the best one. They just choose a better one. And they can repeat arbitrarily. Any one of them can do it in arbitrary order or however. And this thing is going to converge to the optimal solution.
So when you said all entities of the same type apply the same action, you mean at every step? Because they could change the action at every step.
So in the in the history, there is many individuals of a given type will be created. Everybody is using the same policy, the same action.
At every point in time.
Every time that a green creature is generated, it chooses always the same action.
That's the optimal. Yeah.
There is an optimal policy like that.
Yeah.
There could be another optimal policy that mixes, but there is always an optimal
And the
policy.
local search algorithm may not find that.
Yeah, no, it will find an optimal one. It will converge to an optimal one. So basically, that says you can restrict to a finite set of policies, because every type has a finite set of possible actions. So the search space now is the cross product of these actions. So the local search algorithm, you start from an arbitrary policy. Everybody independently may look what they are doing and what everybody else is doing. Could I have done something else better? If I could, I choose the better one. And as I said, you don't have to choose the best one. The other does the same thing. They keep going like that. It's going to converge to the optimal solution. To an optimal solution.
But the better you said, if it can switch its action and improve its extinction probability.
Right.
So it has to be able to compute its extinction probability.
Right. Or if we are controlling the process, we do the computation. So let's say if you decide, I'm going to raise the temperature or, administer this medicine to that one or not, we do this computation.
So it's not like an evolutionary process because it has to be able to make some prediction in the future, rather than something.
It has to see how well it's going to do with the way that everybody else is, with what everybody else is doing. Right. Yeah. So it's not like an evolution. I should say, actually, it's an evolution of some sort, but where they don't compute obviously extinction probabilities, unless there is some other implicit way of doing it. But anyway, so you can do it this way, but in general, the worst case, it could take an exponential amount of time to converge. It's not trivial. This depends on, follows by some actually recent results by other people on macro decision processes. But so actually, we want to compute them directly. So let's write the equations. What are the equations that this best extinction probability satisfy? So the purely probabilistic is the same. So in this example, we have to, let's say if we want to maximize the extinction probability, the equation for this process would be choose the maximum of the green best value and the green brown and the best brown value. So in general, if you have several actions, everybody wants to choose that action which will maximize this the value of the expectation with the values of the descendants. So what the optimal extinction probabilities will satisfy these equations, will be the least fixed point of these equations. Now these equations are, we see they use probabilistic polynomials and also the max operator, if we want to
over monomials.
Over monomials, if I had this case, or if I had mixed and I had this has some actions which have some probability, could be over polynomials.
And what happens to the norm when you do this?
Sorry?
The norm, the things still add to 1?
So every probabilistic polynomial sums to 1 the coefficients, right. And we have max operators in front of them also. So let's say if the green had 3 actions, there would be maximum of 3 polynomials like that. So the equations in general will look like that. Will be a system of n equations in n variables, where every equation says x sub I is max of some probabilistic polynomials. So this, the number of probabilistic polynomials is how many actions are available there, how many choices. Okay, so that's for maximization, same thing for minimization, if we have a minimizing case. Defines against a monotone operator, has a least fixed point, and the least fixed point is the value we are after, the best value. So how do we solve those? Well, kind of we have a hint from how we did it before. So first we find out what's the 0 values and the 1 values. 0 values is again easy. The 1 values is now more difficult. Basically, you have to say, in a sense, say what action should I choose so that the matrices I'm going to get, some of the matrices I'm going to get, will have eigenvalues 1 or more. And that's, for some subset, and then do that more. So I won't say what the algorithm is exactly. It's not that simple, but basically it's a kind of an iterative algorithm which first you try to figure out what are the obviously 0 values and 1 values just from the max and the means and the dependencies between the variables. So you figure those out, you take them out, then in the remaining ones you set up a set of linear equations to look if there is some more that you could set to 1. You solve that linear program. If it has, the linear equations have the solution, that gives you some other variables that you can set to 1. You set those to 1, you trace again implications. If you are stuck, you set up a new set of linear equations, inequalities, solve those, and until you exhaust all the variables. So it's basically repeated use of solving linear programming, solving linear equations, and kind of tracing implications. And that's, I won't go through the details, but that tells you who are the values that are going to get 1 for sure. You can get 1 for sure. And then once we have done that, the second part is, so the theorem is we can get the optimal values in polynomial time in the input size and the bits of precision. Then we do kind of a generalization of Newton's algorithm, but now with the max and the min operators. Of course, max and min are not differentiable, so what do I mean by Newton's algorithm with that? The idea is that sort of it's the same idea of what Newton does. You are at a current solution, you linearize your system, you take your polynomials and do a first order linear approximation of them. So you pretend that they are linear, and then trying to find the best, trying to solve the system given that you have the linear approximations. So if you do that, then to find the next solution, it turns out to be a linear program for maximization problem or for a minimization problem. So you do a linearization of the polynomials and then solve a linear program, and the solution to the linear program gives you the next point to recurse on. And you just follow that, do these iterations, in each step you have to round down the solution also to a multiple of where you keep only so many bits, polynomial number of bits, so that the numbers don't blow up. And the theorem is that, again, a linear number of iterations in the input size and the precision you are looking for is going to get you the right number of bits of precision of the optimal values. The analysis, again, is not trivial, but basically it's kind of trying to tie it down with what the optimal strategy is doing on its own system, and proving that what this is doing, it's kind of tracking what the optimal, if we knew the optimal solution, how Newton would operate on the system with the optimal strategy. This is kind of tracking it at the same time. It's keeping pace with it. So when it finishes, Newton finishes with the optimal strategy, this one is going to finish also and get the right precision. In terms of finding the optimal policies, we can find, for any epsilon, we can find epsilon optimal policies. So policies that are within epsilon of optimal in the value, in time polynomial in the size of the input, and log 1 over epsilon. For the maximization case, there is some problem. You cannot find exactly optimal. So remember, the search space is now restricted to be finite because everybody is going to choose one optimal action. So there is an optimal policy, but in general, it's hard to find the very best optimal. Again, modulo it amounts to the same difficulty about doing unit cost operation on large numbers. And basically, the reason that you cannot find the very best policy is that it may be that there are policies which value, the extinction probabilities are extremely close to each other. So they differ by doubly exponentially small amounts. So you can't really tell the difference between how well two policies are doing because they are just so close to each other. So you have to contend with epsilon optimal only.
So you have this nice result that the optimal policy in this case is deterministic and time invariant and so forth. You think that would apply not only for avoiding extinction, but for other objective functions?
I think it's likely, yeah. So we could define it with other objective functions, which brings me to the next conclusion slide. Okay, so we looked at extinction probability, so that's one thing you can measure for the most basic thing you can measure for, would like to know for branching processes, and for the optimizing the extinction or survival for the cases where you can actually affect the future, or they can affect their future. So then other things you can ask is, how about other quantities you would like to compute? Like Nick said, maybe what's the distribution at a finite amount of time? What's the complexity of that problem? Or optimizing such objectives, for example, minimizing. Let's say if these are bad strains of the sort of drug-resistant cells that you want to kill, minimize their quantity after some finite amount of time, or any number of other objectives. One, for example, could be minimize the total number of descendants of a given type. So you don't like green creatures; you would like to kill them as soon as possible. To have as few of them as possible. So minimize, for example, the expected number of them. Suppose you can have a strategy that's going to kill them eventually, but you want to have also as few of them. That you can do in polynomial time, so that's a different algorithm. When you want to minimize, for example, the expected extinction time, sort of kill them as soon as possible, that I don't know how to do, so that's an open question whether you can do that. And then a number of other quantities you could, or objectives that you could define for them. So that's, there's lots of other questions you can, this is basically the most basics, but there's other interesting questions to pursue. There's then extensions of the, this is a basic model where you just have mutations, and you may have other extensions of the models, these basic models, and there are actually variations that people have looked to model other situations, so that go beyond the basics. So one would be what Sampath asked, where you have both creatures that we want to minimize and types that we want to maximize, and there is then like a conflict that's happening. So we have actually looked at this problem. So you get then like a branching stochastic game type of situation, and for that's we don't know how to solve that. So that relates to an open, basically well looked to open problem, so-called Condon's problem in theoretical computer science, where in the finite state, so these things define infinite state processes. So branching processes defines an infinite state Markov chain. The branching decision process defines an infinite state Markov decision process. And then if you have both maximizers and minimizers, you have an infinite state stochastic game. So even for the finite case of the stochastic games, we don't actually know how to solve them. In the sense, there is no good algorithm that can tell whether we can get, for example, the probability, there's a value to that game, so there is an equilibrium solution. And computing what's the value of the game, even approximately, we don't have a good algorithm for that. This problem, if we go to the infinite state, is actually even more difficult in the sense that even the case of computing the value for the finite state case, we can reduce even to the case of just determining the value 1 for the game. So this is even the qualitative problem, which we know how to solve in the finite state case. When the value is 1, we know how to solve in the finite state case. In the infinite, in this case of the branching case, is at least as hard as Condon's problem. So it's kind of NP intersects co-NP, it's PLS. We don't know how to do it. So that's another open question. So there is, more things to learn about them.
I have a question going back to the simple branching process. So if I condition on null extinction in infinite time, so then there's a stationary, well, except in the generic case at least, there's a stationary distribution. And I would like to know properties of that distribution.
Yeah, so that we pretty much know pretty well from the theory of branching processes. It's pretty much the left eigenvector, let's say in the positive regular case, it's the left eigenvector basically gives the direction, and there is some, and the limit is that times some random variable. Yeah, so it's, that's...
But you can actually get the distribution? Or?
We know what it will be concentrated along the left eigenvector. Right, the actual distribution, I mean, more things, you know, that's basically there is work in the theory of branching processes that sort of tells us a lot about that.
So in Condon's problem, I guess the probabilistic polynomials that arise are all linear polynomials.
Right,
so does that not buy you any, does it make any difference?
No, no. So the linear case here, if we here, so if we have in a sense, the finite state case, the Condon's problem, corresponds to the special case where here everybody has, in every situation, has only one child or no child. So it's a very special case like that. Of course, in general, we can have non-linearity because of the multiplication.
So you used Newton's as a heuristic. Very often when you use Newton, there's a simpler version which would be gradient descent. Have you used a gradient descent algorithm? Didn't work?
We didn't try, but I don't think
okay.
it's good to do.
And the other thing is, sometimes in this situation you might be can use random playout. So it's sort of, you have your path so far and then you sort of randomly play out given the information you have first, and then you sort of optimize based on the random playout. Have you tried that?
I don't know. We didn't try with random playout, but I don't know how to try it either.
Thanks.